Here we go, chapter 12, stoichiometry applications. We've talked about stoichiometry at multiple times throughout this course. So some of this stuff will be review. A lot of it should be review. Does anyone off the top of their head know what we're talking about when we talk about stoichiometry? Yes. Would anyone like to share what we mean when we're talking about stoichiometry?
Is it the example that really helped me was the BLTs?
Yes, it's like in the BLTs.
Yes, so it's basically what an equation or what we have, and it's in different compartments, and we try to see how many we have of that to create something else.
Yeah, it's sort of like how many ingredients do we have, how are those related to each other, and how many products would be produced. For chairs are a nice easy example because most chairs, in this one chair, if I broke this up into chair pieces, I would get 4 legs out of it. There's 4 legs per chair, so if I have, let's say, 10 chairs, I would have 40 legs. Right? That's all that we mean when we're talking about stoichiometry. It's just how are the different things related, and the things are typically involved in a chemical equation. So our balanced reactions give us a numerical relationship in whole value numbers, 1s, 2s, 3s, 4s, etc., between our reactants and our products, and we can use those to convert between our chemicals. For example, if we want to know how much nitrogen do we need to completely react with 3 moles of hydrogen, our goal is to go from the hydrogen to the nitrogen. Since we're already in moles is what we're going to be working with when we're doing stoichiometry. Since we're already in moles, it's a straightforward conversion. We can do that in one step. 3 H2s, or 3 moles of H2, reacts with 1 N2, or 1 mole of N2. And so we get this ratio, this conversion factor, of 1 N2 out for every 3 H2 put in, assuming that they're completely reacting. So we take the 3 moles that we were given, multiply it by its conversion factor, the H2s on top, the H2s on bottom, those would cancel out. And so we're left with 3 divided by 3, that's 1 mole of N2. Hopefully you saw that and you thought, this is easy, I get this, I understand this. That's kind of the most basic scenario for stoichiometry. If, using that same equation, if 2 moles of ammonia are produced, how much of each reactant was used? This is a little bit more complicated of a scenario that we can drum up. Our 2 reactants being the N2 and the H2, and the thing that we're starting with, being the product, is the NH3, the ammonia. So we've got 2 things that we're going to do, and it's the same steps. Even though it looks like we're working backwards, and that might seem confusing, it's the same steps. We're not doing anything really different. It's just a little bit of maybe confusion of exactly grasping what's going on here. But the steps, the math part, is exactly the same. We're starting with the number that we were given, the 2 moles of NH3, and we're going to 2 other chemicals using the coefficients. So we can pull out conversion factors. 1 NH3 is produced for every 3 H2 put in. That's one way that we could come up with that conversion factor. If you look down here, I've got it written in the slides, the reverse. If you flip the top and bottom, it's the same thing. It just works a different direction. It's like dividing by this instead of multiplying by this. I wrote it out so you can sort of, like, this is what's actually happening. Let me space that out so it looks like I didn't write 3H2 Putin. Okay, so that's one of our conversion factors, and the other one is also 1 NH3 with 1 N2. Those one-to-one conversion factors are really nice and convenient because it's just the same number. So when we do the multiplication for these, in both cases we're starting with our 2 moles of ammonia. We're multiplying it by the conversion factor. What we're doing is converting the chemical. So we'd write the 3H2 on the top, the NH3 on the bottom. This is so that the chemicals cancel. So we're switching chemicals. The things that are left are 2 moles and 3H2. They're on the same line, and so we're multiplying them. Multiply by things that are on the top. So 2 times 3 equals 6 moles H2. And for the other one, we're also starting with 2 moles of ammonia. We're multiplying by 1. I would include this when I'm writing out calculations. It's just a formality because the number is the same. So like on an exam, you can skip that step probably. It might be helpful to write it out so that you know what you did. When I go through and take the tests, just because I want to see how hard the exam was, for example, like if it was really tough, I'll go back and take one of the exams, and obviously it's going to be easier since I put it together and see all the questions. I write out all of my work. I was doing this last week with one of my 1A exams, and I had to stop myself because I was like, I'm spending way too much time doing all the work, writing out every single unit, every single number. It's helpful, especially when you're doing exams and you come back to do your test corrections or like, hey, what did I do here? Why did I get this answer? What went wrong? If you have it all written out, then you look back and okay, here's the steps that I did, and then you can identify where you went wrong. If you don't write stuff out, then you're just guessing. Okay, that was going to be a different slide. So those were our stoichiometry basics. Any questions about what we were doing with that? Great. So our limiting reactant is an important calculation. It's not so much important for us, but if we go on to do chemical work, it's important to know what your limiting reactant is. Usually, one thing costs more than the other. If we're doing a simple reaction and we've just got 2 things, let's say we've got, I'm just going to call them A and B because I don't want to come up with chemicals in my head. Let's say we've got 2 chemicals, A and B, that we need to do our reaction, and that'll make C. We know what the ratio of these 2 things are. Let's say we have 2A that we need to put in for every B. We could just shovel a bunch of stuff into our reaction vessel. We could just toss in however much A and B that we want, and then some amount of C will come out. If we don't care how much C we have, that might work. Usually we care about the amount that we're putting in and the amount that comes out. When we do reactions in real life, we're not going to get probably 100% usage of these components. Even if we put in 2A and 1B, we might only use 90% of our B and 90% of our A. Or we lose some of our A, right? So we run out of, like if we're making BLTs, maybe while we're cooking up the bacon, a couple of those pieces of bacon fell into our mouth on the fork. And so we just end up a couple pieces of bacon short. We might want to account for having a couple extra pieces of bacon. The reason that this might matter is A might be $1,000 per gram. Unfortunately, not an unrealistic amount for some chemicals. If B is $1,000 a gram and A is $10 a liter, which one do we want to make sure that we aren't using extra of? B, right? We want to make sure that we're only using as much B as necessary, and we might throw in a bunch of extra A if it's easy to remove. That way we've got plenty of A around. Any of the B that's in there will react, and we're getting our money's worth out of our $1,000 a gram chemical. This is why this might be important, or it might just be hard to remove one of them. So in the lab, we'll measure out our amounts, and if we want to find limiting reactant and theoretical yields, we get to add 2 steps on top of that basic stoichiometry that we were doing earlier. A lot of this should feel like review. So if we have this reaction of solid titanium metal with chlorine gas to form titanium 4-chloride, what are the limiting reactant and theoretical yield given some starting amounts? So what we're going to do is start with both of these, or start with each of them, our 1.9 moles titanium, our 3.5 moles chlorine gas, and figure out how much titanium 4-chloride can we make, TiCl4. An assumption that we're making when we do these calculations is that we have plenty of the other thing. It's just way easier to do it that way. So we'll figure out how much titanium chloride each of these makes. Whichever is smaller is the reactant that runs out first. The one that runs out first, that's our limiting reactant. If I'm putting together chairs and I don't have enough backs or seats or whatever to make chairs, you can't just stick 4 legs out and say, here's a chair guest, sit on these 4 chair legs without a seat or without a back, right? You have to have all of the parts to make a full chair. You'll have leftover parts otherwise. And we're going to have leftover parts when we do chemical reactions, almost all the time. So basically what we're trying to figure out is which one's going to run out first, which one's going to stop us from making more chairs. So what are those limiting reactant and theoretical yields? So starting with titanium and chlorine, let's do the titanium part first. So we've got 1.9 moles titanium. Again, we're starting in moles. It's just more convenient that way. We don't have to do as many calculations. We need to find our ratio between titanium and the product. So we look to our balanced equation. Underlined in blue, we've got invisible coefficients of 1. So we produce 1 TiCl4 for every 1 titanium that we put in. 1-to-1 ratio makes for some really easy math. We can produce 1.9 moles of TiCl4, starting from our titanium. So if everything works out perfectly, if we have enough chlorine gas, that's how much TiCl4 we can make. We might not necessarily have enough chlorine gas to make 1.9 moles of titanium chloride though. So that's why we're going to calculate for Cl2 as well. So 3.5 moles Cl2. And what's our ratio for chlorine to TiCl4? 2 chlorines to 1 titanium 4 chloride. We put, again, the TiCl4 on top, and we put the 2 Cl2 on the bottom. This is so that our chemicals cancel. Right, so the Cl2s cancel. This means we're dividing 3.5 by 2. 3.5 divided by 2 should be 1.75 moles. So what does that mean that we got 1.75 moles? Can anyone interpret that? It's our limiting reactant. Why is it our limiting reactant? It's the smaller of the two. It's the one we can make less product. So again, the assumption that we were making with this calculation is that we had plenty of the other thing. And so if everything went right and we just cared about the chlorine that was involved, this is the most that we can make just based on our chlorine. This amount is smaller, so we're going to only be able to make 1.75 moles. We wouldn't get to this 1.9 because the chlorine would run out first. That's what this 1.75 being smaller is. So our chlorine runs out first. Cl2 runs out first, or will run out first. It limits the product we can make. The chlorine is stopping us from making 1.9 moles of titanium chloride. So that's why it's what we call our limiting reactant. And this 1.75 is then our theoretical yield. It assumes that everything goes perfectly. All right, one for you to try. Consider the following reaction. It's already balanced for you. If you begin with 2.4 moles of sodium and 1.3 moles of fluorine, what is the limiting reactant? And what is the theoretical yield of sodium fluoride in moles? All right, we're looking for the limiting reactant. That means we need what?
The theoretical yield.
We will get the theoretical yield at the same time. What's the limiting reactant? Just generally, what is a limiting reactant?
Whatever runs out first.
Yeah, it's whatever runs out first, whatever makes the smaller amount of product. So starting with the two amounts, the 2.4 moles sodium, 1.3 moles fluorine. We've got two conversion factors we need to find from our balanced equation. We're going to get one for sodium to sodium fluoride. We produce 2 sodium fluoride for every 2 sodium that we put in. A 2-to-2 ratio is the same as 1-to-1. So 2.4 moles sodium fluoride is our possible yield starting from our sodium. Our other conversion factor is from fluorine gas, F2, to sodium fluoride. And again, 2NaF goes up top, and the invisible 1 in front of our fluorine goes in the bottom. So 1.3 moles times 2, 2.6 moles sodium fluoride. So we choose the smaller of the two. That is our theoretical yield. And sodium is the limiting reactant. Question?
How did we get 2.6 from dividing 2 with 1?
1.3 times 2. So this 1.3 moles F2. For a lot of problems, we'll actually be going all the way through to grams at the end. You can always stop if you have the same product. Right? You can always stop at moles without doing the extra multiply by molar mass to get to grams. You can always stop here because moles and grams are going to, if one's bigger, the other is going to be, I think you get what I'm saying. You can always stop here and save yourself doing one more step, or you can go all the way to grams. It really doesn't matter. Either case will get the same reactant and theoretical yield. If you're looking for a theoretical yield in grams, you will have to do that extra step, but up to you. Speaking of grams, with moles, it was kind of easy, maybe, to just like look at it and figure out, okay, well, that's our theoretical yield because we're just doing simple multiplication or division. When we're starting with grams, and in this case we'll be ending in grams, it's not as easy to see, and so it's more important that we write out our calculations. So we're adding a couple steps. We're starting with grams. So 53.2 grams sodium. Can we use this directly with our balanced equation? We cannot. What do we need to use our balanced equation? Moles. And how do we get from grams to moles? Molar mass. So we'll look up the molar mass for sodium. It's about 23. 22.9. 99. We're going to divide by that because in molar mass, the grams is on top. If we divide, that's the same as flipping it and multiplying. Grams cancel. Now we're in moles. And now we can do this step with the balanced equation that we were given. So sodium to sodium chloride, it's a 2:2 ratio. That's convenient. 2 NaCl out for 2 sodium that we put in. I'm going to just cross those 2's out. It'll save us a little bit of time putting it into our calculators. And we could stop here to assess for limiting reactant. Or if we don't mind putting a little bit more into our calculator, then we can just multiply by molar mass, which I'm calculating up here in the top right corner. Ooh. 58, there we go, 0.44 grams per mole. That's our molar mass for NaCl. And the moles, these red strike throughs, the moles cancels the moles that we had earlier. The sodium also would have canceled. So the units that we've got left are grams and sodium chloride. So that'll give us some amount of grams NaCl. Questions about doing that? Where we got the numbers from, why one number's on top and the other's on bottom. Okay. We get 135 grams sodium chloride. So that's about half of the work. We also have to figure out how much we can make from our chlorine. So we'll do the same process. 65.8 grams Cl2. Our molar mass for chlorine is 70.90 grams per mole. 2 times 35.45, 70.90. That'll get our grams to cancel. And then these next two steps should look very or fairly similar. We're going to have the 2 NaCl on top, because that's the coefficient that goes along with sodium chloride in our balanced equation. Instead of having a 2 on the bottom with Cl, though, chlorine in our balanced equation doesn't have a coefficient. That means it has a coefficient of 1. So 1 Cl2 on the bottom. And we get to use the same molar mass for salts, sodium chloride. And I'll just strike through a bunch of stuff. The end result is we've figured out how to calculate our grams of sodium chloride. So we multiply everything along the top and then divide by the stuff on the bottom, and we end up with 108 grams of sodium chloride. So even though we started with a larger amount of chlorine because of the difference in molar masses and some other factors, we ended up being able to produce less sodium chloride with our chlorine. That means that which of these two is our limiting reactant? The chlorine. So Cl2 is the limiting reactant. What is our theoretical yield? 108 grams sodium chloride. Questions? All right, your turn again. And then we'll get into some stuff that I think is new. This new order is kind of throwing me off. All right. We are being asked to find the maximum amount of ammonia given some starting amounts. What does that mean that we're looking for? In the context of previous questions, what are we looking for? We're looking for the theoretical yield. That's the maximum amount that can be synthesized. A common mix-up that I see students make here is we do our limiting reactant theoretical yield calculations, we get two numbers, and they pick the bigger one. And that's wrong because we use up the other one before we can get to that bigger amount. So what we're looking for here is theoretical yield. That's the maximum amount that we can make. The way we're starting these is just like we've started the other ones before. 25.2 grams N2, 8.42 grams H2. To be able to do stoichiometry, we need to be in moles, so we have to convert these from grams to moles. So we're going to divide by their molar masses. About 28 grams per mole and about 2 grams per mole. That'll get both of these into moles. And then we need to look at our balanced equation to get our ratios. In both cases, we're going to be going to 2 NH3, either from 1 N2 or from 3 H2. So we've got a 2:3 ratio for hydrogen. We've got a 1:2 ratio for nitrogen. So 2 NH3 over 1 N2, 2 NH3 over 3 H2. That does the fun job of switching our chemicals, so I'll cross those out. At this point in the calculations, we've got moles of ammonia. If you do things one step at a time, you could stop here, figure out which one's limiting, and then continue from that one. I just plug it in all at the same time. It's not that much more work to just do the extra step. So the last step, we're going to multiply by what?
The molar mass.
Molar mass, which is 17.02-ish. That'll get our moles to cancel, and we get two numbers out. So we get to plug a bunch of numbers into our calculator. So for the first one, 25.2, I'm putting in times 2 times 17.02, and then dividing by the 28.014. We get out 30.6 grams NH3. It doesn't matter which way you put the numbers in, as long as you do the operators correctly. For the second one, 8.42 divided by 2.016 times 2 divided by 3 times 17.02. we get out 47.4 grams ammonia. Again, we're looking for the maximum amount of ammonia. Which number is that, 30 or 47? But 47 is bigger. But 47 is bigger. We're looking for the maximum amount, right? So we want the bigger number, right? No, we don't. We want the smaller number because our nitrogen will run out. We won't have any more nitrogen to be able to get to the 47.4 grams. Nitrogen runs out once we've made the 30.6 grams. That's why we're picking the smaller one. Nitrogen's our limiting reactant. This is the most that we can make. We won't have any more nitrogen to be able to make that much ammonia. All of the good analogies are baking related, and I don't have any recipes off the top of my head. So, sorry. Is it not 17.02?
I don't know. I might have been because I multiplied it by 2 and then added it. So I think I did it wrong.
0.03. Yeah, just the, so for the NH3, okay. Questions about our stoichiometry basics? Hopefully, review, hopefully, easy. It will show up on the final exam, I guarantee it. Have we talked about enthalpy change? Because I legitimately don't remember. Perfect. This is the new material for chapter 12. It's not a ton. So chemical reactions can be exothermic, meaning that they emit thermal energy, they emit heat, or endothermic, meaning that they absorb heat or they take in heat. Can anyone think of another word that has exo in front of it? Exoskeleton. I'm glad nobody said exodia. Because I don't know how to connect that. Right, exoskeleton. What has exoskeletons?
Insects.
Bugs, creepy crawlies, right? That means that their skeleton is on the outside skeletons. We don't have our skeleton on the outside. We've got our bones mostly on the inside, except for our teeth. That's still sort of on the inside, but you can, anyway. When you're brushing your teeth, you're brushing your skeleton. So, exoskeleton, it's on the outside. Exothermic, the heat is on the outside. It's going out, losing heat. Endothermic, all the endo things I think are gross that I can think of, so we're not going to talk about things that have endo in front of them. So these are our two types of reactions. You should know what exothermic and endothermic mean. we can measure the amount of heat, of thermal energy, from a reaction, and it's a function that we call enthalpy. Enthalpy, or heat of reaction, is given with this symbol, delta for change in, the H for, let me do this, change in, H for enthalpy. It's okay if your brain thinks heat, because I think that's what my brain thinks as well. And then the RxN, because we're getting a prescription. I'm just kidding, it's of the reaction. So that delta H sub Rxn, the change in enthalpy or heat of the reaction. There's a detail that's not particularly important for us, is that this occurs at constant pressure. Again, not a particularly important detail for this class. That delta H sub Rxn, the change in enthalpy of the reaction, can be positive or negative. The sign on these, the way that we think of them, is sort of like in a physics model. We've got a system, a thing that we care about, and then we've got the surroundings, the things that are outside of the system. So this positive or negative is with respect to the system. And the analogy here is like money, like on your bank account. Your money, or your bank account rather, being the system. If you see a positive number, you open up your app for your banking account if you have a bank, and you see a positive number, what does that mean? You got paid, right? Somebody gave you money, possibly for goods and services. So positive means money went in or was added. Money is our analogy for heat or enthalpy or energy. Negative means money was taken out. Again, money being our analogy for heat. You went to the salon, you went to the barber, you went to the zoo, you paid your friend because you lost in fantasy football. Whatever the situation, it's a negative dollar amount. So the positive, that's like our endothermic. If it's a positive sign, it's endothermic. If it's a negative sign, it's exothermic. The money's leaving, the energy is leaving. Here's some pictures from the book that might help you with that. Endothermic, energy going in. System energy increases, like depositing money in the bank. Exothermic, energy is lost, System loses energy. Questions? Confusions? Okay, an example of an exothermic reaction is anything that produces heat. Combustion reactions come to mind for most people for exothermic reactions. If we're doing the combustion of CH4, that's methane / natural gas, just to help connect this. So if you're grilling at home and you have a gas grill, this is what you're burning. This is the reaction that you're doing. So you're taking your methane, it's coming out of a pipe, hopefully, into your grill, and then it combines with oxygen, and you have to use a spark to get that reaction going, and then it releases heat, a lot of heat, and some of that heat goes to igniting more of the methane. So it's a cyclic process. The products are CO2. One of the reasons that you don't want to cook inside too much without having a fan on or a window open, because that CO2 is not great for you. And there's also water that gets produced, because it's a combustion reaction. This delta H of reaction is the little thing that we're adding on, right? We haven't seen that before on the side of a reaction. And there is secretly, but not so secretly, a per mole sort of thing hanging out with that. Sort of. So what this tells us is negative means exothermic. Exothermic means heat is emitted or lost from the system being the gas that's burning. So 802.3 kilojoules is produced as heat, and we can use this like a stoichiometry step with 2 moles of O2 or 1 mole of CH4, like it says in that last bullet point. For endothermic reactions, it's the opposite. The reaction absorbs 182.6 kilojoules when we're producing nitrogen monoxide from N2 gas and O2 gas. So the reason that there's like sort of that per mole is because the amount that you react, just like the amount of wood that you put on a fire, changes the amount of heat that comes out of the fire. If you have like 2 little logs on a fire, that'll produce enough heat maybe for like 1 or 2 people to sit around. If you put 15 logs on the fire or some, real big pieces of wood, then you can get a big bonfire and get a whole circle of people warming up around it. And the same is true for our reactions. The amount of heat that comes out or goes into the reaction depends on the amounts of the reactants. So we're doing some stoichiometry with that. It's always going to be specified, that delta H RxN. It'll be off to the side like we saw it previously. And we can use that delta H sub Rxn in stoichiometry. we're going to see examples of that. Here's one of those examples. So if you're grilling outside, you're using propane and possibly propane accessories. Most outdoor grills use LP, liquid propane gas. Liquid propane is C3H8 as a liquid instead of a gas. And you react that with oxygen to produce CO2 and H2O because it's a combustion reaction. The delta H of the reaction is given over here on the right, like I said it would. I promised you it would. What this means is that, do we have examples? We do have an example. I'll do another one here. Let's say that we've got 4 moles of C3H8. We can use this minus 2,044 kilojoules as one of the things in our little ratio that we produce with the coefficient on C3H8. So this minus 2,044 with the 1 C3H8. What we're looking for in this problem that I've just made up on the fly is an amount of heat that's going to be released. Which of those two numbers that's underlined in blue do we want to be on the top? Kilojoules. So minus 2,044 kilojoules over 1 mole C3H8. So if we burn 4 moles of propane, we would expect to produce 8,352 kilojoules of heat. It's a full day's worth of calories, apparently. Questions about getting any of those numbers, where they came from, where they're going? Yes?
When I multiplied 4 by the negative 2,044, I got 8,176.
Oh yeah, I did times 8, sorry. What was the number? 176. It's a problem with mental math. We can also do a slightly longer calculation if we start with grams. So we are reacting ammonia with oxygen according to this equation. It's balanced. We've got coefficients. And the enthalpy of the reaction is endothermic or exothermic? Exothermic. It's a negative. That means it's releasing heat. We're starting with 97.32 grams of ammonia. We're going to burn it. What's our first step? Yeah, we want to figure out our molar mass. We did that one earlier. I believe it was that number, 17.031 grams per mole. So we'll divide by our molar mass. That converts us from grams to moles. I know that a lot of people like doing them in single steps, so we'll do it in single steps. So 5.714 dot 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 moles of ammonia. What's our next step? Ratio. Yeah, so then minus 906 kilojoules and the for ammonia. We produce 906 kilojoules for every 4 moles of ammonia that's put in. So times minus 906 and divide by 4. Minus 1,294 kilojoules. Is that our final answer? Do we have the correct units? Yes. Okay, great. Final answer. So all we've done really sort of is add two definitions. Exothermic heat is going out. That corresponds to a negative sign on our delta H of the reaction. And endothermic energy is going in. That means you need energy to fuel the reaction. That would carry a positive sign instead of a negative sign. And we've added that we can use this number as one of the things in our ratio. So that's kind of the 3 things that we've done that's new in this chapter. All right, we've got a little bit of time. Give this one a shot. To save you calculating the molar masses, there's all the molar masses you might want and more. Would anyone like to share their answer? If you've got one.
Negative 89.62 kilojoules.
-89.6. Anyone get a different answer?
Don't be scared to disagree. There's a high likelihood of that being wrong.
I got the same answer, but I feel that we left the step out, because I didn't do anything with the O2.
Okay.
The excess, and then I reread the question, it says excess oxygen.
Right.
So
Yeah.
I'm like, oh, I think I'm supposed to do something like that, but.
So we're starting with this 58 grams of sulfur dioxide. Sulfur dioxide is SO2. We leave off the mono on the sulfur because it's just one. We're going to divide by our molar mass to convert us into moles. We're preparing to do the stoichiometry step. Anytime we're doing a stoichiometry step or a ratio step with these numbers, we need to be in moles. So that's why we're doing this molar mass step. And then the two numbers that are relevant for us is the minus 198 kilojoules and the 2 SO2. So we put the minus 198 kilojoules on top. That's the unit that we'll end up with. And on the bottom, 2 moles SO2. The moles SO2 cancels the moles SO2 that we had before. And we should end up with minus 89.6 kilojoules. There's a question, though, about what does excess oxygen mean here? All that excess oxygen means is that it's not our limiting reactant. We have plenty of oxygen. We're not worried about, are we going to somehow run out of oxygen before we can burn it all? We've got tons of oxygen that's just around, and so this is just telling us that sulfur dioxide is our limiting reactant. We don't have to worry about anything else. We can just do the problem normally. For most people, the excess oxygen probably doesn't matter to you. You would have just assumed that anyway. People that write these problems put them in just so that other people can't be like, well, but what if we ran out of oxygen first? What if we didn't have any oxygen? So that's why that's there. Any questions? Great. So that was chapter 12.